Let's talk about hypothesis testing fundamentals. A statistical hypothesis is a statement about the parameters of a population or its related distribution, for example, the mean and the variance. We're going to talk about several of these types of parameters that we can use in hypothesis tests. A statistical hypothesis test is formulated as a pair of hypotheses. We have a null hypothesis. This is the base case hypothesis, which generally cannot be proven but only rejected. You can never accept the null hypothesis. You can only reject it or fail to reject it. It would be similar to in science, where you have a theory. You might hypothesize that something is true. You can never prove with 100% certainty that something is true, but you can accumulate overwhelming evidence that supports that it's not false. So we never accept the null hypothesis. We can only reject it or fail to reject the null hypothesis. An alternate hypothesis is a case that we propose. You can either reject or accept the alternate hypothesis. An alternate hypothesis always carries with it a certain risk of error, and this is known as alpha, or a type 1 error that we'll talk about in a little bit. The null hypothesis we oftentimes denote as H naught. It's a parameter equality. You cannot prove true, only reject or fail to reject. H1 is the alternate hypothesis. It's usually a parameter inequality. It's generally greater than, less than, or not equal to. The first of these two, greater than or less than, are the most practical and most common when we perform hypothesis tests. Let's take a look at the possible forms of hypotheses on the mean. As an example, mean could equal 4. We could have a two-tailed test where we say, as our alternate hypothesis, the mean is not equal to 4. So that's known as a two-tailed test because we're looking at greater than or less than 4. A lower-tailed test would be our alternate hypothesis, mu is less than 4. And in order to accept this, we have to show that our sample mean is significantly less than 4. And we have an upper-tailed test where we hypothesize as our alternate hypothesis, mu is greater than 4. So I've got a question for you. Going back to our example, Elish Gardens claims that the bumper car ride lasts 3 minutes, but you think that it is significantly less than 3 minutes. Which of the following correctly shows the hypothesis test that you would set up for this situation? The correct answer is D. The null hypothesis is always an equality, so it has to be equal to something. The alternate hypothesis is an inequality. Elish Gardens claims that the mean is 3, but you propose, or your alternate hypothesis is that the mean is less than 3. So let's take a look at this. The null hypothesis, mu equals 3. Alternate hypothesis, mu less than 3. If y is the random variable representing bumper car ride time, and the distribution of y is normal with mean 3 and variance 0.05, the average of a sample of y, this is the distribution of y bar, containing n equals 5, will have a normal distribution with mean 3 and standard deviation of sigma. Sigma is the square root of 0.05 divided by the square root of n, and that's 0.1. So this would be the expected distribution of y values. By the way, if y is our random variable, sometimes you'll see the hypothesis written as follows, where our null hypothesis, mu y equals 3, and the alternate is mu y less than 3. So we have the subscript y there. If sigma is known and the null hypothesis were true, we would expect the distribution of y bar to be centered on mu equals 3. It would be improbable to get a sample with a y bar value in the yellow range. So getting a value of y bar down here is pretty rare. That probability can be termed alpha. It's a risk level, and it's represented by the yellow area. If we did get such a sample average, if we got a sample average down in the lower tail in this alpha region, we might claim then that the alternate hypothesis is true, and we would reject the null hypothesis. And this is in fact what we do. If we come up with a sample average that is down in this tail, we have evidence that the null hypothesis is false or incorrect, and we can accept the alternate hypothesis. However, there is a risk that we might be wrong. It is possible, based upon just the random and statistical nature, there is a probability that we would get a sample average down in the lower tail here in the yellow region, even if the mean really is 3. If that happens, it's known as a type 1 error. In other words, we concluded that the alternate hypothesis was true. when in reality it is not true. So there's always a risk level when we talk about doing these hypothesis tests. We can pick alpha with a very small value, for example 0.1%. The risk of a type 1 error would be pretty small, but the y-bar value would have to be quite small to justify rejecting the null hypothesis and claiming the alternate hypothesis to be true. So if alpha is really small, it's going to be very difficult to ever accept the alternate hypothesis. However, with a large value of alpha, if you expanded alpha, we might easily conclude that the alternate hypothesis is true. We would reject the null hypothesis when in fact that's not the case. In other words, we have allowed the risk of a type 1 error to be too large. So there's sort of a trade-off between making alpha too big and alpha too small. In science and engineering, we typically use alpha of 0.05. That's the most common. It's a 1 in 20 risk. And sometimes you'll see 1% and 10% risk levels used. It's quite common to perform hypothesis tests on the mean. We're going to explore both cases, whether variance is known or unknown. We can also put together hypothesis tests on the variance. We can hypothesize the variance is equal to some value or greater than, less than, or not equal to some value. We can also perform hypothesis tests on a binomial proportion. So maybe you think that a coin is rigged and you think that it's coming up heads a lot more frequently than just 50%. You could put together a hypothesis test on that. We can put together hypothesis tests on the difference in means, so two different populations. Here we have the difference between the mean of A and B is equal to 0. That's our null hypothesis, or it's greater than 0. Alternatively, we can write this as mu1 equals mu b by moving mu b to the other side, or mu a is greater than mu b. We can also look at the variances of two different populations. We can compare if they're different, if the ratio is equal to 1, or they're not equal to 1. We can rewrite this one as sigma squared of a equals sigma squared of b, or not equal to. I mentioned earlier that two-tailed tests are not that common. When you're comparing two variances, this really is the only exception where a two-tailed test is quite common. In the next screencast, I'm going to show you how we can use confidence intervals to perform hypothesis tests on the mean.